Hello and welcome to our 8th lecture. This is on exponential functions. We're now skipping into chapter 2 in the book, which will deal with functions. So again, we're laying the groundwork to get into the calculus content, which will be next week. We're not having a whole lesson dedicated to functions themselves, but I do want to give a brief refresher. Think of functions as like a machine or an assignment. It's this process where you assign an input, x, you assign it to a unique output, which we call f of x. So this very process of assigning an input to a unique output, this process is a function. This unique part is important. It means that for any input, you get just a single number as your output. So something goes in, only one thing can come out. For example, we often describe functions in this way based on what happens to your input. So you plug in x, you plug x into f, and your output will then be that very x plus 2. Now we call this a linear function because it represents a line. It's a degree 1 polynomial. Suppose I plug in the number 1, then the output would be this, f of 1. So you just substitute 1 in for x. F of 1 is 3. So 1, your x, is your input, and then 3 is that unique output. Likewise, I could plug in negative 2. Well, then you add 2 to that to get your output, 0. So functions can be graphed, and the way it works is that every f of x pair is represented by a point on the graph. So we know that 1, 3 is a point, 1 is the input, and 3 is the output. And these were just 2 points I discovered. There are many more, but we're not going to write all of them. So these are points on the graph. Y equals x plus 2. Notice that y is taking the place of f of x here. So that's what happens when you graph. So the outputs correspond to y values, and the inputs of the function correspond to x values. So that's all I wanted to say on functions generally. They will be a big part of the class when we get to derivatives, which is coming pretty soon, a couple weeks. How about a new page? Now our main topic for this video is exponential functions. These are functions of this form. So when determining the output, your input is in the exponent, hence an exponential function. This a is some number, a real number. We want it to be positive, but also not 1. And most of what we're going to look at in this course is a greater than 1, but you can have numbers between 0 and 1, like 1/2. Those will look a little different. Excuse me, let's focus on a standard example where a is 2. F of x equals 2 to the x. This means when I plug in some number x, I get an output or y value of 2 to the x. We'll look at the graph that represents this function. First, let's plot some points. Remember, the y is the output. Let's plot some standard x. And we'll start at 0. If x is 0, then the y value associated with that is 2 to the 0, which is 1. Okay, here we have 2 to the first, 2, and 2 squared, which is 4. With negatives, remember, a negative transports you to the other side of the fraction, if you will. So instead of a 2 or 2 over 1, you have the reciprocal of that, 1 over 2. And likewise, 2 to the minus 2 is 1 over 2 squared, 1/4. Let's plot these points. So let's say this is 4. Just go out a couple units. So my first point I looked at was 0, 1. So x value of 0, y value of 1, that's that point right there. And I plug in 1, then my y value is 2 to the 1, or 2, so we're at a height of 2. And I plug in 2 for x, I get a y value of 4. So we plot a point right there. Now when I plug in -1, I get a height of 1/2. And then half of that next, 1/4. And that's enough to start connecting the dots. This is what it looks like. Exponential functions are known for their rapid growth. We say that something is growing exponentially. We think of that as growing very quickly. And that's reasonable because these things do rise pretty quickly. So real quick, just notice that the y value is always greater than 0. That's a feature of these things. unless you artificially lower the graph. We'll talk about that in a second. But when you have a function of the form that's just a to the x, then you're always going to be above the x-axis. You see, even when we plug in negative x, we still have ultimately a positive number. It just gets very small, gets close to 0. All right, let's look at more complicated one. This is exponential because it has an x in the exponent, but it's of course of a different form. It's not just a simple a to the x. Well, this -1 with the x and also the -2 over here, they are transformations of your graph. Now, we're not dedicating a whole lot of time to this, but I want to mention it briefly. First, this -2. Whenever you are adding or subtracting something that's outside of this exponential part, if we have a -2 out here, that represents a vertical shift of your original graph. Say if we only had this 3 to the x minus 1 part, when I then subtract 2, that means we go down 2 units. So this is a vertical shift, 2 units down. If this were instead a +2, then we would be going up by 2 units. Now this is interesting here. Since there's a -1 that's in the exponent part, that accounts for a horizontal shift. So that is when you're adding or subtracting something within the exponent. Think of it as the -1 is applied directly to the x. So that's affecting things in the x direction, horizontal. This horizontal shift will occur 1 unit to the right. Now, this is a little bit counterintuitive because it's a -1, and yet we're moving in the positive x direction to the right. That's just a hallmark of these horizontal shifts. You have to think a little bit backwards. Vertical makes sense. -2 means you go down. But if you have a -1 with horizontal, that means you move in the positive x direction, 1 unit. So just keep that in mind. Horizontal is weird. You have to think backwards. And if it were instead a plus, say x plus 1, then you would move in the negative x direction to the left. All right, let's graph this thing. Instead of plotting a bunch of points, like making a big table, I would start with the basic version of the graph, namely the basic exponential function 3 to the x. Right, that's what you have before you start throwing in all these vertical and horizontal shifts. So the basic graph of 3 to the x, 3, 2, 1. Okay, so when you plug in x equals 1, you get a height of 3. When you plug in 0, you get 1. And then at -1, we get a height of 1/3. Notice that this is growing faster than the first graph we looked at, 2 to the x. And that's normal when you have a bigger a bigger base. That's taking up maybe a little too much space. So let's apply our transformations. I actually want to start with the -1. 3 to the x minus 1. Then we'll add the -2 at the end later. This moves us 1 unit to the right. So now I have the point 2, 3. And the point 1, 0. Or excuse me, 1, 1. And a height of 1/3 here. So I just shifted 1 unit to the right. And now we throw in the -2. Hope I can squeeze it on here. We take our previous graph and move everything down 2 units. So before, we were always just above the x-axis. Well, now that bottom has shifted down 2 units. So I'll draw a dashed line to represent that. That's our floor, if you will. So we're just above that. We have this point. And instead of a height of 3, now that's gone down 2 to 1. So, moral of the story, when you run into these complicated exponentials, just think of it in terms of starting with the original, most basic version, some h to the x form, and then think of it as applying transformations. Now let's talk exponential equations. So if I have equations involving exponentials, that means my variable x will be in the exponent. So how do we deal with those if we want to solve for x? Here's the main trick. If I have a common base on both sides like this, then that means the powers must be equal. And this is, of course, assuming the normal things about this a, positive and not equal to 1. Let's look at a couple of examples. And we want to solve, which means we find the number x which makes this work, or perhaps there could be more than one. The trick is to get a common base. We don't quite have that yet with 9 and 27, but both can be rewritten with base 3. Think of 9 as 3 squared, and 27 as 3 cubed. Now, with just a little bit of extra work, we'll have something where both sides are base 3, and then we can work with that. Remember the exponent rule? We multiply these things when you have a power to a power. 3 to the 2x. Now this times 3 is happening to the entire quantity x plus 1. So you have to distribute the 3. That could be a common mistake that could be made. So focusing on the ends, now that we have the same base, that means that the powers are equal. 2x equals 3x plus 3. And now this is merely a linear equation, so a lot easier to solve. I'll subtract 2x from both sides. I should do that in a different color. So we can get x by itself. And while we're at it, let's also subtract 3 from both sides. So this will become an x, and we'll be left with a minus 3 over here. Great. Last problem. Now this one is a little harder to see how you can get a common base. At least that's true at first. But once you know the trick, it's not too bad. So I don't have to reduce 6 at all or factor it in any way. You don't have to do that. But rather rewrite 1. Remember, anything to the 0 power is 1. And now we can proceed. We have a common base of 6, which means those exponents are equal. Now this is quadratic. So I like to factor that. So this part could be 0, which means that x would be 1, or this part could be 0, and x would be negative 1. This has 2 solutions. See you in the next video, where we will talk about logarithmic functions. These are pretty closely related to exponentials. They're like a backwards version, if you will.